Section 15.5, Damped Simple Harmonic Motion. So this is where we're going to make things a little more realistic, at least dipping our toes into it. We won't fully dive into this. That would be a more advanced physics or engineering class, but at least introducing the idea. So what is this damped simple harmonic motion? Well, if we have an external force reducing the motion of the oscillator, we say its motion is damped. Typically, we just assume that there is nothing reducing the motion of the oscillator, that we have this ideal oscillator that could go forever. So one possible illustration of a damped model is that we have our mass on the end of the spring that could go oscillate forever, except for there's this vane attached to the end of it, just something that has to pass through water. And if it's getting dragged up and down through the water, that liquid is going to exert a damping force. We're going to assume that the damping force is proportional to the velocity, which is reasonably accurate for slow motion. As you get going faster, you get higher order terms, like the velocity cubed starts to play an effect. And this damping force is similar to the drag force, if you remember that, since that one also was proportional to the velocity. So we can say this damping force, F sub d, is equal to negative b times v times the speed that it's traveling. B here is a damping constant, so it depends on the shape of the vane, the viscosity of the fluid, right? You would expect a very different result if it's passing through water versus if it's trying to pass through honey. So the damping constant B is something that's usually either given to you or you might have to solve for it, but more often than not, it's just specified directly. So we could use Newton's second law with this extra term and rearrange to find this factor. So what we have here is we have our spring force, right? Hooke's law, the negative kx, and we have negative bv as another term. Here, I'll start writing these out. Negative b times v, negative k times x. Those are our two forces, and it's from F equals ma, right? So those are the forces. They're equal to the mass times the acceleration. Well, we're going to add those negative forces to the other side, so they're on the same side as acceleration. Then we're going to write everything as a derivative of position with respect to time. So acceleration becomes the second derivative of position with respect to time. Velocity becomes the first derivative position with respect to time, and x stays x. Some things don't change. So this is now a differential equation. So if you take differential equations, or if you have taken it, you could solve it to get this result. And the key difference here from what we had before is this extra damping term. And because we have this extra term, it just modifies our solution to the differential equation slightly, where our position as a function of time will still be x max, and it will still have cosine omega t plus phi. The real big difference is that now we have this exponential decay, e to the negative bt divided by 2m. That the amplitude, everything in front here is the amplitude is going to get smaller as time passes. The other slight modification here is that the angular frequency is slightly modified. That's why it's omega prime. Prime in our textbook isn't a derivative. It's just saying modified. So the slightly modified angular frequency can be found with the square root of k divided by m minus b squared over 4m squared. Right, so continuing on with these ideas, if the damping constant b is fairly small, then the modified frequency is actually pretty close to the natural frequency. You can see this at a glance with the equation up here, that if b is small and then we square it, that's going to be really small compared to k, the k over m term in front. And so we can then say that, yeah, the frequency will be approximately equal to our default of k divided by m, which is the natural frequency of a mass on the end of a spring. Also, assuming it is small damping, we can find the mechanical energy by substituting in our new decreasing amplitude. So instead of using xm squared as before, we're going to do xm times e to the negative bt over 2m, and we're going to square both of those because we're plugging it into 1/2 k times the amplitude squared. So xm is squared and the exponential term is also squared, which is why the 2 in the denominator disappears, because it is squared away. All squared away. Fantastic. I'm sure that means you understand it all perfectly. Here's a really nice visual of this. So we see our same cosine function as before, but as time passes, notice the amplitude is getting smaller and smaller. It's still oscillating with the same period, it's just decreasing with that slow exponential decay. So let's try an example of this, because I know it can feel a little bit abstract. So a damped harmonic oscillator, time to decay. For the damped oscillator shown, mass is 250 grams, K is 85 newtons per meter, and B is 70 grams per second. A, what is the period of the motion? B, how long does it take for the amplitude of the damped oscillation to drop to 1/2 its initial value? C, how long does it take for the mechanical energy to drop to 1/2 of its initial value? Right, so I've already started to draw this, and I'm going to jot down these last parameters as things that we know. Actually, I can do it right on here. So M is 250 grams. See, K is 85 newtons per meter. And B is the 70 grams per second. Okay, and then also we can jot down what we want to find. So in part A, it asks for the period of the motion, so that's going to be t. In part B, it's asking for how long. So what parameter would be how long? That should be time. It's asking how much time is required. But the condition here is for the amplitude to be 1/2 its initial value. So amplitude halved. And then part C is again how long, so it's also asking about time. But now it's about the mechanical energy being halved. So time required for the energy to be 1/2 of its value. All right, so now that we have those jotted down, I'll stop sharing so that you can see this a little bit bigger. One thing to note is they gave us the mass and the damping constant in terms of grams, but we know grams is not our SI unit. So even though they gave it to us and it seems like it should be fine, we want to switch to SI units to always be safe. So 250 grams, I would write as 0.25 kilograms. And for B, 750 grams per second, I'm going to move the decimal place over 3 for the kilograms, so 0.070 kilograms per second. All right, so we first want to find the period, and we have an equation for the angular frequency, right? We know the modified one is that it is omega prime is the square root of k over m minus this b squared over 4m squared, I believe. Let me double check. Yes. Now, is this a case when we could use the natural frequency instead? That it's just equal to the square root of k over m? Are these equal? Well, I say we check it out, because why not? At a glance, looking at it, B is very small of 0.07 compared to K is 85. So my guess is that this is going to be one that's small enough. But it doesn't hurt to plug and chug. So we'll do it the full equation first. So omega prime is equal to the square root of k, which is my 85. I'm going to drop my units for now just to be compact. 0.25 minus 0.07 squared divided by 4 and 0.25 squared. The only reason I felt safe dropping the units is because I did check that they were all SI units before I plugged anything into that. All right, now let's check, because I don't actually have this number. Okay, so I got that basically this is 340, and this second term, this is actually a really good way to do it, is we should just do it in two different calculations. So 340 minus, so just to highlight it, I'm going to do it all the way out, divided by 4. The second term is 0.0196. So it's tiny. That's not going to do anything when we take the square root of it. So this is a case when we could use just the simple square root of k over m. So that's pretty nifty. So we can find our angular frequency is the square root of k over m, which is 340. And so if we take the square root of that, then that would be 18.44. Angular frequency has units of radians per second, but notice we are solving for period here. So this is not yet period. So period is going to be 2 pi divided by this angular frequency. Because it's the inverse of the linear frequency or the cyclic frequency, and then the 2 pi to get rid of the radians per second there. So if we go ahead and plug in 2 pi divided by this 18.44, which I'll just use my inverse button on the calculator. So I get 0.34 seconds. I could maybe, yeah, we have 2 sig figs here, so I'm going to leave it at that and not go to 0.341. All right, so there's part A. Sweet. Now, what about parts B and C, where we find the amplitude is half as much or the energy is half as much? Well, for this, we're going to need to think about our amplitude equations. So our amplitude equation is going to become from xm times the exponential e to the negative bt over 2m. So that's the amplitude at any given instant in time. And we want this amplitude to be equal to half of what it was initially. So the initial amplitude, so 1/2 of xm times really e to the 0, because we're plugging in time is equal to 0. And e to the 0 is just 1, so it's just the initial amplitude is just x max. So now we notice if we're solving this, we have xm on both sides. Because we're getting a fraction of the initial amplitude, it doesn't actually matter how big the amplitude was initially. That part just cancels out here. So we can divide that out. And then we have an exponential is equal to 1/2. So to get rid of the exponential, we can take the natural log of both sides. Sorry, that's getting a little messy. So if we take the natural log of e raised to stuff, all of the exponential power will come in front, the ln of e will cancel out, and so we get negative bt over 2m is equal to the natural log of 1/2. Oops, and we're getting a little too low there. There we go. So to solve for time, I'm going to multiply both sides by negative 2m over b, and then we'll basically be home free. So negative 2m times ln of 1/2 divided by b. And we're glad that there's a negative sign there. This can feel a little scary, having a negative time, but it's the natural log of 1/2. Because it's the natural log of something less than 1, this is going to give us a negative value, and it will cancel out. And so if we plug in our mass of 0.25 kilograms, and our B of this is 0.07 kilograms per second, what we'd find is that the kilograms are going to cancel out, and the inverse seconds in the denominator will become seconds. And so if you calculate that out, you should get 5.0 seconds. So relative to the period, since the period is basically 1/3 of a second, it's going to take about 15 oscillations before the amplitude is half as big. Now, what changes for part C, where we want to find where the energy is half as big? Well, for energy, we have a slightly different expression. For that one, remember, it is related to the 1/2 kxm times the exponential squared. So 1/2 kxm e to the xm squared, e to the negative bt over m, where I've lost the 2 in the denominator of the exponential because that term is squared. And we want this to be equal to 1/2 of the initial value. So 1/2 of 1/2 kxm squared, where the exponential disappears at time is equal to 0. So both of these have the same 1/2 kxm squared, so that part doesn't actually even really matter. And we're left with something that looks really similar, e to the minus bt over m is equal to 1/2. And so the only thing that's different here is that our exponential term is twice as big. It's missing a 1/2. So I'm going to skip a few steps and jump to the end result here, but I'm happy to work through the algebra with you if that is helpful. What we end up getting is we lose a 2. So the e becomes negative m, natural log of 1/2 divided by b. And indeed, our time is half as big, 2.5 seconds. All right, so that got a little bit low there, but that walks you through the entire solution. A little bit lengthy, and it's mostly because our equation is a little more involved. We have this exponential term. The frequency is potentially a little bit different, but the math isn't actually all that scary once you get past the fear of having an exponential term in there. Exponentials are really not the end of the world, I promise. So let's share the screen once more so we can see the end result. Right. So here it walks through and it gets the exact same answers for the period, for the time, for the amplitude to drop, and for the energy to drop. So energy is lost more quickly than amplitude. Right, if I haven't lost you yet, let's take a look at a checkpoint. So there are 3 sets of values for the spring constant, damping constant, and mass for the damped oscillator. Rank the sets according to the time required for the mechanical energy to drop to 1/4 of its initial value, greatest time first. This is a problem that requires some careful thought, so I encourage you to think about it. See if you can come up with a result. So please go ahead and hit pause now. Okay, did you hit pause? Well, before we get to the end result, I do want to highlight this in case it's helpful, that we have that the energy depends on this exponential. And so I made a plot of some various exponentials, e to the minus 1/2 x, e to the negative x, and e to the negative 2x. So these show trends, but they don't match the sets given, just telling you up front. But it might help you as you're thinking about this. So with this added information, I want you to think about it some more, see if it confirms your idea or if it gives you something else to think about. So go ahead and hit pause now. Did you do it? Okay. Well, the key here is noting that the exponential is what causes the amplitude to decrease, right? The K just sets how much energy there is initially, but since we're looking at the drop relative to its initial value, the K doesn't actually matter all that much for the rate at which it's dropping. All that we care about is this exponential, which can be written as e to the minus b over m times t, where t is our variable. So depending on the b over m value, you'll get a different result. So notice set 1 is just b over m. Okay, that's cool. Set 2 is 6b over 4m. So that's 1.5 b over m. And then similarly, set 3 is 3bo over m. So that's 3b divided by m. So that's worth noting that, hey, look, this fraction is getting bigger as time goes on. What happens as the power gets bigger? Well, it's going to drop faster. Careful here in the question, though. It's going to drop faster, but it wants us to put the greatest time first. The one that will have the greatest time is the one that takes the most time to decrease to 1/4 of its value. It's going to be the one that has the smallest exponential drop-off. And the biggest one will come last. So what does this mean? Well, let's take a look. So the answer is A, because set 1 has the smallest exponential power, so it takes the longest to decrease in amplitude, versus set 3 takes the least amount of time to decrease in amplitude because it has the largest power. All right, so this was a mouthful. I'm happy to talk about it further. If you have questions, please ask away. Let's discuss this some more.